Remember those word problems from childhood, the ones that hide a system of equations? Algebraically, you could crack them in about a minute, but this is the moment where computational thinking really clicks. Instead of solving by hand, we hand the computer a pile of candidate values, tell it to test them against the rules, and print the answer. Here's the example. Elisa, Ben, and Cindy are selling tickets to a fundraiser. Ben sells 2 fewer than Elisa. Cindy sells twice as many as Elisa. In total, they sell 10 tickets. The question is, how many did Elisa sell? We could untangle this with algebra. But the computational approach is different. We turn each sentence in the problem into a rule, then let the machine try every combination of ticket counts and report which one obeys all the rules at once. First, we generate every possible combination of ticket counts using 3 nested for loops. The outer loop walks Elisa through 0, 1, 2, and so on. For each value of Elisa, the middle loop walks Ben through 0, 1, 2, and so on. And for each of those, the innermost loop walks Cindy through 0, 1, 2, and so on. Because the loops are nested, every Elisa value gets paired with every Ben value, and every one of those gets paired with every Cindy value. So we sweep through combinations like Elisa 0, Ben 0, Cindy 0, then Elisa 0, Ben 0, Cindy 1, covering the entire grid of possibilities. Now we encode the problem's relationships as Boolean conditions. The first condition is that Elisa plus Ben plus Cindy is equal to 10, the total tickets sold. The second is that Ben is equal to Elisa minus 2, the 2 fewer relationship. The third is that Cindy is equal to 2 times Elisa, the twice as many relationship. We join all 3 with logical and so the check passes only when every relationship holds at the same time. Inside the innermost loop, whenever a combination satisfies all 3, we print it. Running this prints a single line. Elisa sold 3, Ben sold 1, Cindy sold 6. Let's confirm it by hand. 3 plus 1 plus 6 is 10. The total checks out. Ben's 1 is indeed 2 fewer than Elisa's 3, and Cindy's 6 is exactly twice Elisa's 3. The code found the answer for us by testing, never by solving algebra. 2 things stand out about this approach. The upside is flexibility. If the problem changes, say Ben now sells 3 fewer, or the total jumps to 50, we tweak a number, run it again, and the new answer appears instantly. We never redo the algebra by hand. The downside is speed. The work grows with the size of the numbers. Suppose the total were 1,000 tickets. Now Elisa runs from 0 to 1,000. And for every Elisa value, Ben runs from 0 to 1,000. And for every one of those, Cindy runs from 0 to 1,000. That's 1,000 times 1,000 times 1,000 combinations, roughly a billion checks. 3 nested loops over large ranges quietly explode into an enormous amount of work. We can do far better by mixing a little algebra with the computation. Notice that once we pick a value for Elisa, the other 2 are completely determined. Ben is Elisa minus 2. Cindy is 2 times Elisa. So Ben and Cindy aren't free to vary, which means 2 of our 3 loops were never really needed. Let's see how the total collapses. The total is Elisa plus Ben plus Cindy. Substitute Ben as Elisa minus 2 and Cindy as 2 times Elisa. That gives Elisa plus Elisa minus 2 plus 2 times Elisa, which combines to 4 times Elisa minus 2. Set that equal to 10. Add 2 to both sides to get 4 times Elisa equals 12, then divide by 4 to find Elisa equals 3. The same answer reached with algebra instead of a billion checks. Here's that insight as code, and it needs only a single loop. We loop over Elisa's possible values from 0 up. Inside the loop, instead of guessing Ben and Cindy, we compute them directly from Elisa. Ben is set to Elisa minus 2, and Cindy is set to 2 times Elisa. Then we keep just one check, the total. If Elisa plus Ben plus Cindy is equal to 10, we print the trio. Running it prints the same answer. Alyssa 3, Ben 1, Cindy 6. The crucial difference is the work. The brute force version did about 1 billion checks for a total of 1,000. This single loop does about 1,000. We folded 2 loops into a couple of assignment lines, and the program now finishes almost instantly. Step back and look at what we did. We took a word problem and solved it 2 ways without ever solving it the way you learned in school. First, brute force. Turn every sentence into a Boolean condition and let the computer test candidates until all the conditions hold. Then we refined it. Spot that some unknowns are determined by others, use a pinch of algebra to eliminate the redundant loops, and shrink the work from 1 billion operations down to 1,000. That blend described the problem as rules the machine can check, then reason about the structure to make the search cheap. It's the heart of computational thinking. It's the mindset worth carrying out of this course and into every problem you meet. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.